All right, so we proceed further, covering more of the effect of process parameters. So, what did we do? We had looked at various essential components of a draw texturing machine and possible machine profiles to ease the working, effect of time and temperature, and also in this context we tried to understand if there is something called rate of setting which can be defined. And we also understood that the rate of setting is not very specific to a material. It can vary within the same material also, depending upon how much draw you are doing, what temperatures are you processing, and so on and so forth. So, we shall continue our discussion on other parameters, which are the process parameters. So, these two in some sense we have finished. We were discussing something on the draw ratio, d by y ratio, and what we learned was that the d by y ratio essentially is related with the twist being inserted into the yarn, and this twist insertion is not linear, and so there are slips as you keep on increasing the d by y ratio. And also we found that because of this, the tight spots increase exponentially after a certain value of the d by y, and therefore one has to worry about the number. This number could be expressed obviously in numbers per unit length. The unit length you are expecting is kilometer. So, some numbers per kilometer of a yarn, and this number should not exceed a certain value, could be 50 per kilometer, lesser the better. Beyond this, there will be client is not going to be happy with the quality of the textured yarns. So, remember we are now talking about not the crimp rigidity, which of course is important, but in the case of friction texturing we are also interested in the quality which is being characterized by the tight spots. So, we were somewhere here and we tried to argue in some way, maybe did not. The behavior, so the broken filaments are concerned, as the d by y increases, the broken filament level decreases. In some way it is a silver lining. Same parameter, when you increase, one characteristic falls and the other characteristics increases, and therefore you have a reason to be at an optimum d by y ratio. So, we wanted to understand as to why the broken filament level, which also could be expressed in numbers per kilometer or something. So, we would like to see why does this happen. So, before we answer this question, let us see, we look at another relationship, if at all exists. If you remember, when we said the d by y ratio increases, the twist level increases, we also said something will be happening to the tension in the filament. Now, a tension which is measured in the twist zone is the T1, which sometimes is also known as the input tension. So, if we want to approximately draw a curve of T1 as the d by y ratio increases, what kind of a curve do we expect? You must remember that when we increase the d by y, we are trying to insert more number of helices per unit length. If everything else is constant, the draw ratio is constant, time temperature is constant, then what would happen to the T1? Will it increase or decrease? Increase? Right. So, let us say there is some increase in T1. But as we said, in a false twist friction texturing, we are also interested in what happens to the output tension. This word input or output is in relation to how the yarn is entering the twister and exiting. So, we can measure tension T1, we can measure tension T2. So, what do you think should be happening to T2? Yeah? Increase. So, when we say increase, let us say T2 will increase as T1. Yeah? Decrease? Decrease? So, this is curve number 2, this curve number 1, we are talking about T2. So, anything else? Yeah? Exponentially increases. Anything else? First increases and then levels off. So, seemingly a simple question has different answers, and the answers are quite different. So, that means it appears that nothing is as simple as you talked about T1. So, let me see if we got an answer for somebody who said it will decrease. So, can you tell us as to why would it decrease?
Because there is detwisting is happening, that's why tension will decrease.
Okay. So, his argument is that as you move out of the twister, the zone before the twister was a twisted yarn, and as you get out, there is a detwisting taking place. If the detwisting takes place, the tension in that zone can reduce. Looks good? The yarn is moving over a disc. Invariably, whenever you move any yarn over any material, so based on this wrap angle, if this is T1, the T1 and T2 are related with friction and the wrap angle. Invariably, T2 may be high in this case, but our case is different. The yarn is not just passing over something called a disc, it is also twisting and also simultaneously untwisting. At one area it twists, in the other area it untwists. If twisting means increase in tension, untwisting should mean opposite of that, right. So, this is surprising, but not so surprising. That means the T2 actually can follow a curve like this. That is, when either it is not rotating, then T2 is going to be high. If the disc does not move, only yarn is moving, you can do that. You can always stop the disc rotation, and if only yarn is moving, so there is only friction which is working. So, whatever is the tension below, the tension above could be more, right. But as you increase the twist level, so we are expecting detwisting level also will increase. So, as you keep on increasing the d by y ratio, the tension in the output zone keeps on decreasing, right. Is there that part clear? No questions about it. Now, we can try and answer this question. Why the broken filaments are found to be less as we increase the d by y. What do you think? So, we just went and tried to understand what is happening to T1 and T2. Does it correlate in some manner? So, at least one thing is appears that the broken filaments are more dependent on the T2. Why should it happen? Because after untwisting, you have a parallel bundle of filaments. Before it is a twisted yarn, one single unit, they behave like a single unit. So, when any rough weather, like for example slippage and other kind of thing happen, now individual filaments have to withstand the torture. So, nobody else is supporting now. If the fellow happens to be at the wrong place at the wrong time and tension is also high, then it will break. Like for example, when the d by y ratio is less, T2 is high, filament is individual and gets a rough end, slippage occurs or something, it just breaks. But as you are increasing the d by y ratio, more twisting is taking place, therefore, more untwisting is taking place, tension, output tension is reducing, therefore, broken filaments reduce. Good for us. So, this is in some way gets related. So, what becomes important for someone is to find out, of course, you are interested in the absolute values also, you will be interested in absolute values, but ratio will be important. This will be an interesting zone where the tension levels are equal, and so an optimization could be thought of. So, what we have is, if you look at the Ts increases like this, the broken filament decrease like this. So, ideal maybe we work here at this d by y ratio, but how do we know, you know. So, what we have is, in case we have some acceptable limit of these characteristics, then you can get a range of d by y where you can do some optimization. So, you have a range, and it will be interesting to see that in this range the tension levels are quite close. So, you get another parameter to monitor. If you have online measurement of tensions T1 and T2 and you find that the ratio is going haywire, you can apply some control. Otherwise, what will you first texturize the yarn, then go offline and measure how many broken filaments and how many tight spots are there, and then come back and change the d by y. That of course is possible, but if you measure tension, which can be measured without measuring crimp rigidity, without measuring broken filament, without measuring tight spots, then you have some correlation which is going to be helping you to remain in a range. So, if we increase the machine speed, let us say I am running at 600 meters per minute and I wanted to go to 800 meters per minute and go to 1000 meters per minute, I am just changing the speed. What it means is you are changing the time, residence time. But then you say, well, my heaters are fine and their length is fine and they can look after, so I run the speed. So, that is one part of it. So, crimp rigidity can be affected if you increase the machine speed. What do you think would be happening here? So, if we increase the machine speed, so everybody will be happy increasing the machine speed, production is higher. So, the difficulty that comes is as you increase the machine speed, this range gets lower, because the curves will change in a manner, because there are vibrations, because the more speed means more vibration and more slippage. When slippage occurs, something will occur. So, you will probably have less leeway on the d by y optimization, but that is okay. If you are accurate enough, you can still be able to do that. So, because we do not have a real good control on the twisting mechanism and therefore, there is a slippage. So, you have an additional problem, and so no one talks about 0 broken filaments and 0 tight spots. You say something will happen anyway. So, you only talk about limits. Okay. If you want to increase the speed, then and also want to have a large leeway, maybe your limits on the broken filament and the thing may have to be increased, but that may not be acceptable to the user.
Sir, what would be the significance of the diminishing effect of this range of dy or acceptable limit of dy?
Well, it is the twist level, and twist level increases has some influence on crimp rigidity also. So, while you are controlling this, obviously it must be controlled, but something else will change. So, it is not that they will be totally independent and you can independently change. The moment you change any of these things, there will be some effect somewhere, and one of the effect will be crimp rigidity itself. But then still people will say crimp rigidity little bit of less, probably we will be able to tolerate, but if broken filaments keep increasing, people will reject even before testing. So, the next parameter which you have some control on is the draw ratio. The draw ratio basically is dependent on what? It is dependent on the residual draw of the POY. So, you do not have too much of a choice here. You can't say, well, I will do only half the draw ratio. That means you are getting a material which will have larger, more elongation at break and of different property. And you can't even say that I will extend too much, because then you will be coming in a zone where breakages can also be there. So, you will have very less play with the draw ratio. If your client says that this is the percentage extension of the textured yarn I am looking at, so we will be doing everything to meet the expectation. So, you will do the draw ratio adjustment or draw ratio in such a manner that the final yarn has a certain acceptable breaking extension. But if you find, well, actually it is going beyond your acceptable limit, then you can advise the person, look, do not worry about extension break at the moment, otherwise this will be there, or optimize in some way or the other. All right. So, despite the fact that we have POY, the draw ratio may be a 10% less than the residual draw, so that even if there is a issue of any migration not taking place properly, you will not be overdrawing any filament. Draw has to be done, so you do not overdraw. You may have some underdrawn because filaments are migrating. So, the migration in this case is not equal to what you would have expected in a fully drawn yarn. It is better than, let us say, the undrawn yarn which we defined. But even if we accept whatever, it is still being drawn. So, when you draw, there will be some filaments on the surface which, if you draw exactly same ratio to the same ratio, then some of them will be more drawn than the others, no doubt about that. So, you will try to minimize that. So, you do not overdraw, draw a little less, and then obviously work around your crimp rigidity, tenacity, etc., elongation at break. But then whether draw ratio also has any effect on the quality characteristics of the textured yarn, we have to see that. So, before looking at that, because we found tension is an important parameter, let us look at that first, which we consider as the T1. If the draw ratio increases, because you are increasing, what will happen to T1? Doubts? Increase the draw ratio, what will happen to T1? It will increase. There should not be any doubt. You are doing nothing except pulling. So, that has to directly result in the increase in tension. Twist was still an indirect method of increasing tension. Here, so it is almost, the more you stretch, the more is the tension. So, T1 will follow this. T2? Yeah? T2 will decrease. It is all based on T2, all right. So, T2 would decrease in the same manner? No? Anyone else? What? It will increase. Yes? Increase? All right. So, there should not be too much of a difficulty in accepting that you are just pulling and there is no nip in between. There is a twisting element and over which you are just pulling, and you keep pulling more and keep pulling more, expecting that tension is going to go down, is too much of expectation. So, the T2 would also increase. The question is whether the T2 will be below T1 or above T1. So, T2 will increase, T1 will increase, but whether it will be below T1 or above T1. Yeah? Above. All right. So, we put above also, T2 star. So, some people are saying above, some people are saying below. So, what do you think? So, both are right. It could be above or it could be below based on the d by y ratio. If the d by y ratio happens to be in the range where T2 is supposed to be high, it will remain high and keep increasing with the draw ratio. If it is in the other zone, then it will remain below and keep increasing. So, effect of draw ratio will result in an increase in both the tensions. The T2 and T2 by T1 ratio would be dependent on d by y, this we know earlier. Not proportional, but dependent. So, if your d by y is optimized in whichever manner, it will run. Obviously, you will like T1, T2 to be as close to each other as possible here also. Now, we know something from the previous arguments that we have done. When we increase the draw ratio, what do we think should be happening to broken filaments? Right? They will increase. Why? Because T2 is increasing. And the increase may be following the T2 or maybe more. So, it will only increase, because when it is T2 they are untwisted yarn, and untwisted yarn the filaments are vulnerable at that point whenever you increase the T2. And the tight spots, so tight spots so they will decrease, increase, increase. So, your broken filament also increasing and tight spot is also increasing. Any other option that you have? Increase, decrease, decrease. So, actually क्या है कि लाइफ में दो ही चीज़ें होती हैं. It could either increase or decrease. Sometimes they remain same. That's the trichotomy. Two quantities, A could be equal to B, A could be less than B, A could be greater than B, and the fourth one is quite difficult to find. But we will have to have a reason for that, whatever you say. Those who actually thought that it should increase, what are the reasons? You know what a tight spot is. So, what is the likely reason? Anyone? More slippage due to tension. More slippage. Anyone else has any other curve and an argument for that? And a curve and an argument? No curve, no argument? So, you accepting? Yeah? So, this is not right. Doesn't happen. What you will get is like this. That is, you increase the draw ratio, the tight spots are going down. Again, good for us. One of them is increasing, the other is decreasing. So, we have a way in which we can get our optimum value somewhere. But the question is, why does it decrease? Why does it decrease? Number of helices decrease. That should reduce the crimp rigidity. Why should it reduce tight spot, if that is true? So, for tight spot you got to obviously remember what is a tight spot and why does it occur. Yeah?
It's inserted.
Right. So, real twist gets inserted. Why does it get inserted? Because there are slippages. You are assuming there are slippages, therefore, real twist get inserted. So, by increasing draw ratio, why is it reducing? Now, when you increase tension, whichever tension you are looking at, which means draw ratio, what would happen to the normal force? Because normal force is related to frictional force and related to torque. because this is at some angle, therefore, there is a wrap. If you have a wrap, then if the tension is put increased in the yarn, this would result in more normal force. And what will be the result of this? The result of this would be better contact. The result of this would be less slippage. The result of this would be also more twisting, maybe. So, draw ratio is giving effects opposite to that you have observed for a d by y ratio. So, the tight spots decrease, which is also a good thing for us, and in general, therefore, we again have a situation where the tight spots which are here, they decrease, the broken filaments all right. So, they increase, and so you again have a limit where you should be able to optimize the draw ratio. That means, you may be able to meet the client's requirement also, and if you are not able to meet, then obviously you have a problem. Suppose this range comes in between, then you know quality will be maintained and extension at break would also be maintained. If this range is big, good for us. If range is smaller, then you have a limited way to play around to meet the requirements, because characteristics, the quality characteristics are more important. You cannot obviously do without it. The other effect which we should be concerned about is the angle of wrap, sometimes represented as psi. You think it is a good idea to leave this discussion on you. Now, you know what is a broken filament, why does it occur. Now, you know what is tight spot and why do they occur, and so now you have an angle. But remember, important thing about the angle of wrap is that this angle of wrap cannot be very easily changed. There is a twister and it has a configuration. So, change the angle of wrap, you have to change the twister, because there are guides which may be placed at a certain distances, so that the wrap occurs. Okay. That means, this experiment is more suited to the machinery manufacturer. So, changing an angle of wrap would mean changing configurations, but it does not matter whether machinery manufacturer does this experiment or the texturizer does this experiment. What I meant was that as a texturizer, you would not have an option of very easily changing angle of wrap. Of course, you can change one twister with another twister which has been designed for a different angle of wrap, right. So, in fact, what will happen is that for such and such denier of material, please use twister X, and for the other range use twister Y. But obviously, somebody decided that why should you use this kind of a twister. So, that parameter is a parameter not under your control so much, but the control of machinery manufacturer or the one who designed the twister. But anyway, we should be able to wrap it up sometimes, all right, the angle of wrap. So, I am not doing this, we will see. So, considering whatever happens and whatever we understood, if the tension level, let us say T1, because T2 is related in one way or the other based on d by y or draw ratio, is 0. you are working nicely, and the angle of wrap, which is psi, is positive. So, we have a texturing machine and we have started adjustment of this kind. What will happen? What will happen? Some people will like it because tension is less, therefore setting will be better, molecules will be able to do and go to whichever configuration they want to go. So, what will happen? Will there be twisting? There will be no twisting, no texturing. What are you going to be optimizing? Because it will be only slipping. Because for twisting, you needed some normal force, and just by putting tension and things are happening, and if you just remove tension, things do not happen. Okay. For example, this will be difficult to obtain if the tension levels are reduced to 0. All right. And then second question, what happens if angle of wrap is 0, but there is tension? Yeah. No, there may be contact with the disc. You can always make sure that there is a contact. This is going, it's a point contact. What will happen? No twist again, right? Therefore, in friction texturing, and the kind of friction texturing we are talking about, the tension and psi, which is the angle of wrap, have a definite positive role, and whenever they change, something will change. The amount of twist will change because of tension itself. So, even if you like it, you do not like it, twist getting inserted, because contact will be more. Therefore, the torque is going to be different, the external frictional force is going to be different. So, where do we stand? We stand now saying that there is no positive control in the friction texturing, and slip is inherent because of vibrations which will happen whenever you run a machine, or it may be because of the internal resistance which is equal and opposite to the external torque. The more you twist, the more is the internal resistance. So, whenever two opposing forces work, there can be slippage, which is surging, is what we talked about. So, there is a slip. The quality characteristics which need to be optimized, of course, other than, all right, other than time and temperature. Are these three, and these three in some way control T1 and T2 in some way. The third one we have not discussed, but I am sure you can guess they will be controlling, and therefore, we have some way to understand what has happened. The question that remains is, do we have to live with this slip and also the problem, the broken filament, tight spots, surging, etc., and snow generation, because there is slip, right? So, we just look at this problem and then finish today. What is the problem? The problem is that there is a yarn, let us say we are talking only at a point contact, this can be extrapolated, integrated later. At that particular point of contact, the frictional force are acting on this yarn. Let us say the yarn is moving downwards here. So, the frictional force, because of the movement of the yarn, will be upwards, acting opposite the motion. The disc is rotating in one direction, opposite to that there will be another frictional force. So, there are two forces, one this and one this, are at that point acting on the yarn. But because they are two forces and they are vectors, therefore, there is resultant force. Resultant force, which is neither in the direction of the yarn movement, nor it is in the direction of the movement of the surface of the frictional disc. So, forget about the thing that you were thinking maybe it is lagging. Yarn is obviously going to follow, they are moving slowly, disc is moving faster, that of course. But we know that at some stage, if everything is good, maybe it will pick up and get to the same kind of revolution. But what is this? The direction of the frictional force will never be the same as the direction of the motion of the yarn or the direction of disc. And if this is the kind of thing that you are expecting, then you will have a slip, right, because direction motion is different. So, the frictional force somewhere else, the surface is going to be pulled in some other direction. Surface being pulled in direction, the yarn wants to go somewhere else, rotation also happen. Because this difference will exist, and so slip is inherent. Avoiding this in the situation that we have discussed. So, we live with it till the time you optimize, reduce things, but you say, well, I am going to create something in this kind of situation. So, considering this, you will see that there is a slip. So, there is a problem. If there is a problem, there is going to be, you have to keep worrying about it all the time. So, I think we stop here and then we will pick up from here next time.